students, we have been discussing about ternary phase diagrams, and I just started discussing about the basics. The last time I have discussed about the isothermal sections and also the tie lines, rules and regulations of the tie lines for the ternary sections. Today I am going to talk about vertical sections and as well also polythermal sections, and we are taking examples of ternary isomorphous system in which all the binaries are forming simple isomorphous type phase diagrams. So, therefore, the phase diagram in the ternary space is basically like a two curved surfaces bounding the liquid plus solid region. So, now let us look at the again little bit recap of the isothermal section, so that you do not forget it. As you know, this is what is this ternary isomorphous phase diagram bounded by the two surfaces, liquidus and the solidus, and the top is above the liquidus surface you have liquid, below the solidus surface you have solid alpha, in between you have liquid plus alpha, just like a binary section. And I have been drawing this one again and again to make you sure that you understand it very clearly, correct. So, this is the binary space diagram and correspondingly ternary is like that. So, now as you have seen that this is a very simple ternary phase diagram, and we can actually look at the three dimensional model and understand, but there may be situations where the three dimensional model is very complex, and because of that we need to look at the projections. And one of the best way of taking projection is taking sections at some constant temperature. Suppose if I take the section at temperature, different temperature is called isothermal sections, and isothermal section is shown here. If I take isothermal section at temperature T3, it will look like this. Basically, if I take the way I do it, I take a plane parallel to the horizontal Gibbs triangle or Gibbs triangle at the bottom, I take a parallel triangle and cut the three dimensional model using that triangle. And if you look at carefully, this triangle will cut the liquidus surface at L1 and L2, solidus surface at S1 and S2. Now, if I project these two curves here to here and these two curves there, and I can actually write down L1, L2 and S1, S2, and this is exactly shown you here. So, therefore, this is basically a projections of the ternary section at a temperature T3 plotted onto the Gibbs triangle, and this looks like what is shown on the right side picture. Again L1, L2 is the projection of the liquidus, which is projected liquidus projection at temperature T3 sorry, and S1 and S2 are the projection at temperature T3, and this basically demarcates the different regions just like a binary liquid, solid and liquid plus solid. And as I told you, here actually we can draw tie lines between these two curves like L1, L2 and S1, S2, and all these tie lines as I discussed will follow certain rules and regulations. That is what we have done. Now, I am going to I am going to go forward. Today I am going to discuss about the vertical sections. The second important section which is used in the ternary phase diagram is called vertical sections. So, those are isothermal and horizontal sections, the one I just discussed. Vertical sections are different types. Okay. Vertical sections are taken perpendicular to the temperature, they are taken parallel to the temperature axis. Okay. So, I can take vertical sections at different ways, in different ways. I am going to show you that. Suppose this is my Gibbs triangle, and I can take vertical sections parallel to the one of the sides like this. This is suppose AB. I can also take a vertical sections starting one of the corners like this, A capital A small c. Also I can take a vertical sections little bit angle DE. There are three important vertical sections normally we take. The first one along AB is shown here. Suppose if I draw a vertical plane This is the vertical plane, let me just draw it for you. This is the vertical plane, right. So, this vertical plane moves directly up, and if it moves, it cuts obviously both the liquid and solid surfaces. As you see, it cuts the liquid surfaces L1 and L2, L1 is here, L2 is there, it cuts, it moves vertically. Similarly, it also cuts the solid surfaces as S1 and S2. Now, I just plot this section along AB. A is starting at a composition, B is starting at, you can see A is basically binary compositions along AC and B is a binary composition along BC, correct. So, they are all not pure, they are actually alloys, this 2 point indicates binary alloys. So, if I plot it, the way it will look like is like this, there will be 2 open ends on the both sides, as you see here, these are the 2 open ends, these are the 2 open ends on the both sides, correct. But it looks like a binary isomorphous phase diagram. Why? Because it will have a liquid above, solid below, and between the 2 curves you have solid plus liquid, liquid plus alpha, what I have marked here. But remember, this is not the case. What I mean to say is that it is not like a binary isomorphous phase diagram. I cannot draw tie lines, correct, like this, I cannot draw. These are all wrong, this is wrong, completely wrong. You cannot draw a tie lines there. It is very clear why I cannot draw. See, if I suppose this is my section, if I draw a tie line, what does it go? It go and hits somewhere else. It does not meet this one liquid surface to the other solid surface, it does not. So, if you look carefully, that is what you have to look, you have to think yourself in the perspectives of the 3-dimensional diagrams, and if you look carefully you will see that is not possible here. I cannot draw tie lines between the 2 solidus and liquid the surfaces which is plotted here, correct. That is the most important lesson you have to remember, that on the vertical sections it is not possible to draw tie lines, only on the horizontal sections I can draw tie lines, and then I can actually formulate rules and regulation for tie lines. Now, let us move on to the other thing, that is for the first thing. Let us move on to the other things, okay. So, therefore, another section we can draw is along AC. A is basically on the ends of the composition triangle, Gibbs triangle, and C is like that. So, that way I will draw it, let me just erase this part so that you can see it nicely. So, the way it is drawn is that I can take a vertical section like this and draw like that. So, if I draw a vertical section like that, it is again a rectangle, again basically it is a rectangle obviously. So, it will cut S here, liquid surface there, correct. So, if you see carefully, the way this can be drawn is like this is basically like this, correct, exactly like this. So, again this will also demarcate regions liquid plus alpha and alpha, just like the previous one, correct. So, thus basically it is possible to show these different regions just like a binary phase diagrams, but here you see one end of these curves are joint, other end is open. So, that means that because it starts from a rich end and it ends at the one of the alloys which is BC on the BC side, or that means alloy consisting of B and C element, it does not have any A, because as I told you the composition sitting on these lines or the sides of the triangle will demarcate, will tell you that they are binaries, okay. So, as very clearly I cannot draw these tie lines here also and do calculation, so these are wrong, not allowed at all. So, that is another way of drawing it, the diagrams. So, I again re-raise and I tell you how to do the next one. Next one, correct, next one is what? Next one is along DE, okay. So, DE will not be like a parallel to AB is parallel to capital AB, small ab, DE will be like this at an angle, correct. So, if I do that, then I take a vertical, like this. You can see here this is L1 star, L1 dot S1 prime, again this is S2 prime, and this is L2 prime. Okay. So, if I draw it, it will look like exactly the way I have drawn for AB. Okay. So, I am drawing it for your purpose here, so that you can understand it nicely. Okay. So, let me draw it properly, so that you understand it properly. So, this is D, this is E, temperature, and this is my L1, this is my L1 prime, S1 prime, L2 prime, S2 prime, liquid alpha, liquid plus alpha. So, it exactly looks like, yeah, it is a little bit not same, because temperature is increasing, that is that way. So, it will be higher, I am sorry, it will be higher. Okay. So, these points will change. Sorry, why it is moving, I do not know. Anyway, this is L2 prime, S2 prime. Okay. Correct. So, that is how it will look like. But here also I cannot draw the tie lines, because these tie lines, if I draw, they are incorrect, wrong. So, the message is that vertical sections can be of three types. One, which is like AB, along AB, it can be a line parallel to one of the sides of the gibbed triangle. Another one is it starts from one end, A end, and it or B end or C end, it goes to the opposite side. And third one is a line which is not parallel to one of the sides, but at an angle like DE. But all of these will not allow to draw the tie lines. That is the very important thing you have to understand. Okay. Anything else I need to talk? Let me see. I am just reading the book which is there. So, it says the same thing, iterating. It is general, it is not possible to draw a horizontal line, tie lines across the two phase regions in the vertical sections to indicate the compositions of the coexisting phases at a given temperature. The only time, let me just read it out, because this is very important, you should remember that. Only time it is permissible is when a section occurs in a diagram which is a truly binary section. Yes, that is possible. Like if I take a binary section, suppose, okay, let me just erase this part. If I take a binary section, why this is moving? Okay. So, let me take, if I take a binary section along, this is a binary section, if I take like that, this is what it is, okay. Then I can draw. Then what I am getting? I am getting like this, then I can draw this tie lines. So, what does mean to say is that? It mean to say is that, okay, let me erase this, this is a problem, or let me just do one thing, I try to get back to you, just a moment. It is creating problem. Insert, let me introduce a slide. Take a moment, please. So, what it mean to say is that if I take a section along this line, it will look like this. It will be looking like this. There I can draw. So, it is only possible when the section occurs in a binary section. So, if section occurs in a diagram which is a binary section, this case arises when a congruently melting compound occurs in one of the binary system, that is possible, yes. This is one way. Otherwise, if a congruently melting compound occurs in the binary section, then also you can do that. The section from the third component to the compound can then be a binary section, usually called a pseudo binary section, and tie line can be drawn on such a vertical section to present the composition of the conjugate phases, correct. So, this is another way, this is one way, another way is that if one of the ends of the section is the corner point and other end is corresponding to a congruently melting compound. Okay. If I on the way, if I when I am teaching it, if I find such a diagram, I am going to come back and discuss with you. So, that is then only you can draw these tie lines, otherwise you cannot draw the tie lines, correct. So, that is about the particle sections. Now, we are going to look at the last thing is the horizontal or the polythermal sections. What is polythermal section? Let us look at it, correct. So, before that let me just go back to you and discuss discuss about the phase diagram here. What is the 3-dimensional plot? Yes, 3-dimensional plot is here. So, I erase this part, why it is not erased anyhow. So, this is the 3-dimensional model as you see here. Okay. So, in the 3-dimensional model we have two surfaces, one is liquidus, other one is solidus. Now, we can use this thing to understand the solidification pathways, how alloy will solidify. Please remember, I have done it for binary, so I will also do it for binary again first and then discuss the ternary, correct. So, what happened to a binary? Let me just draw. Suppose I want to discuss an alloy solidification of alloy Xb0, correct. Obviously, I do a vertical line is like this. Now, please concentrate here. Now, what will happen? Only this is liquidus, top surface is liquidus, bottom surface is solidus, this bottom curve is solidus. So, what will happen? Below only this liquidus, the solid will start forming and I can draw tie lines and follow the things, and finally whole liquid will solidify at this temperature. This is TL, this is TS, right. That is what happens. And you know that if I cool it very slowly like equilibrium manner, then the solid will have a uniform composition. But when I change the cooling rate or I will go for non-equilibrium manner, then it will lead to coring, that I have discussed. Now, let us do that for ternary sections. To show you clearly, what I have done is that I have cut the middle part out. As you see here, these are my solidus and liquidus surfaces. Okay, you can clearly see this is liquidus, top ones and bottom one solidus surfaces. And I am going to follow solidification of the alloy composition X, correct. So, as you know, as they cool down, it will first hit the liquidus surface at L1, correct. So, as it hits the liquidus surface L1 as L, not L1, L will be in equilibrium with the solid composition S, which is sitting on the solidus, correct. As you clearly see that, right, you can clearly see. Now, as you cool down the temperature, the new equilibrium will exist between, it is just like this. Suppose if I have, this is what, this is S, this is L, L1, S1, L2, S2, L3, S3, like that, correct. It goes like that, and this is the S4. Now, so similarly, as you cool down, the new equilibrium will develop between a liquid L1, a solid S1, correct. So, these are the tie lines, or these are the things which you can connect on the, not tie lines, on the solidus and liquidus surfaces. Then as you cool down, there will be new equilibrium exists between L2, S2, L3, S3, and finally at S3 it will solidify, correct. So, now question is this, it is not always possible to track through the solidification pathways from the 3-dimensional model. What you should do basically is to project the whole thing onto the 2-dimensional ABC Gibbs triangle. Okay. So, what we project? We project both the liquidus surface and the solidus surface and draw these lines. So, as you see here, this is the X line which is meeting at point S3. Okay, S3 is where the solidification ends, correct. And then from the S3, a curve originates, move up to S, another one originates, move up to L3, correct. So, what does it mean? This one which is originating from L or S3 whatever they are coinciding each other and moves along L1, L2, L3 is the projection of the liquid surface. On the other hand, the curve which you see here moving from S3 going to S2, S1 and S is the position of the solid surface, correct. So, if I have that in my view on the two dimensional projection, then I can explain the solidification pathways much easily. Let us see how, correct. So, as you can see here S and L they are connected by a tie line, can you see that? Similarly, S1 L1 is connected by that, S2 L2 connected, okay, S3 L3 is connected. So, now I can actually, because these points are lying on the Gibbs triangle, I know their compositions very easily, because each of these points corresponding to a ternary composition because they are sitting on the inside the triangle. So, as I know their compositions, I can easily explain how the solidification is proceeding. I can actually calculate volume fractional phases very easily, which is not possible using the 3-dimensional model. In 3-dimensional model you cannot use these compositional data points and calculate the volume fractional phases or how the solidification is progressing, what are the composition of the solid product coming, you cannot do that. Rather you can do easily if you project these things very easily, correct. That is the idea, that is why actually most of the cases we project even the thing onto the triangle, and this is what is known as polythermal sections, okay. They are actually known as polythermal sections. Why they are called polythermal sections? Because they are actually at different temperatures, okay. See L and S, they are meeting at a temperature suppose T, L1 S1 is T1, L2 S2 at T2, L3 S3 is T3, because they are at different temperatures and all of them we are projecting onto this triangle, that is why it is called a polythermal section. So, therefore, the message which you get, very important message, is that we can use these polythermal sections nicely to demarcate how the composition is, how the solidification is taking place, in fact how the composition of the solid and liquid is changing, correct. Now, this is at equilibrium. Imagine what will happen if you do non-equilibrium. In a binary we can do that, we can draw a dotted line like this, correct, you have seen, right, dotted line like this, or let me draw it better way because you may not be able to see it, a dotted line like that, sorry it should be dotted, so like this, that is how we can explain the effect of non-equilibrium solidification. But can I do it here? Well, that is possible here, and in fact we will discuss little bit in the next class about that, but for the timing just try to concentrate on this polythermal section and understand. So, in a nutshell, before I move on to the non-equilibrium and eutectic phase diagrams, I am going to discuss about eutectics, solidification path, eutectic systems, okay, and different other polythermal sections. You can see here I am going to discuss all this stuff with you. So, before I do that, I just request you to try to understand this particular aspect, especially the isothermal sections, vertical sections and the polythermal projections. Please try to spend more time to understand these, otherwise next all these things eutectic and other 3-phase or 4-phase equilibria in a ternary sections will not be clear understandable to you, and all these things cannot be even discussed in a detailed manner, in the sense that because these requires understanding 3-dimensional sections and the projection onto the Gibbs triangle, and therefore it is important that you have to visualize it in the sense that you can draw this projection yourself and in your mind and then draw it onto the paper. So, that is what is my request to you. Please try to spend time on these so that you can understand them very nicely. So, the next class we are going to discuss a little bit about this non-equilibrium effect, and then finally we will move into the eutectic phase diagrams, okay.